Hello, we're talking about intermolecular forces, the attractive forces between molecules. And the ones that we're going to be interested in this discussion are dipole-dipole, hydrogen bonding, and London dispersion forces. And one way of comparing the strength of intermolecular forces is by comparing the boiling points of compounds, or melting points. And that the higher the boiling point, the greater are the attractive forces, or the intermolecular forces. And that it takes more thermal energy is related to temperature to pull molecules apart. In that, in the solid state, there's lots of attraction. In the liquid state, there's less attractive forces between the particles. And in the gaseous state, there's no attraction between the particles. So let's look at these various examples. The first one, in Table 1, we've got compounds that are all from group 4. And so the one that I've drawn a Lewis structure of is that of methane. There are 4 electron domains around that central atom and no non-bonding pairs. So that means we've got a tetrahedral electron geometry and a tetrahedral molecular geometry for methane. And since they're all group 4, they all share the same Lewis structure. Now remember that this Lewis structure shows how it obeys the rules for writing Lewis structures, but may or may not adequately describe the molecular shape. And that, once again, this is tetrahedral. The bond angles are not 90 degrees. The bond angles are 109.5 degrees. But if you set yourself down on that carbon and look out toward the 4 electron domains, they're all equivalent to one another because they are the same atom. They're all 109.5 degrees. So these are all nonpolar molecules, and the only intermolecular force that they have are London forces, London dispersion forces. And you can see as the molar mass gets bigger, and that's one way of quantifying the size of a molecule, that as the molar mass gets bigger, as we go down the periodic table, those boiling points increase. The larger the molecule, the larger is that electron cloud, and the easier it is to disrupt that electron cloud to have temporary dipoles and induced dipoles in there. So as the molecule gets bigger, the London forces increase and the boiling point increases. Table 2 are the halogens. Fluorine, chlorine, bromine, and iodine. There's diatomic molecular species for all these. And they all share the same Lewis structure as does F2. And since both fluorines are identical, they have the same electronegativity, that means they're sharing those electrons in that single bond equally. But as we talked about in terms of London forces, that there are fleeting instances where the electrons are unevenly distributed that causes partial charges to occur in the molecule, and those can induce partial charges in other molecules. So as the molecules get bigger, the electron cloud gets bigger, it's easier to distort, and the attractive forces will increase. And so as we go from fluorine to chlorine to bromine to iodine, we see the molar mass increasing, we see the boiling point increasing. Fluorine and chlorine are both gases at room temperature and pressure. Bromine is a liquid. In truth and advertising, iodine is actually a solid at room temperature and pressure. That when and it will eventually sublime, as opposed to melting, you'll go directly from the solid state to the liquid state. And so all of these were nonpolar, and they only have London forces associated with them. The next set of molecules are all group 6 molecules with oxygen in the middle. The first one is actually 3 oxygens. And I've got a Lewis structure drawn. It's actually one of the 2 possible resonance structures for ozone. And remember that this may show the way the electrons are distributed, but doesn't show the actual shape of the molecule, the molecular geometry. And that these molecules in this grouping, they're all bent. And since they're bent, they're going to wind up being polar. And being polar, they will have dipole interactions. And so as we go from ozone to SO2 to SeO2 to TeO2, tellurium dioxide, you can see that the molar mass increases and the boiling point increases. From ozone boils at minus 170, and tellurium oxide is actually going to be and for that matter, selenium dioxide. They're both solids at room temperature and pressure. The attractive forces is so great. And so their boiling points are way up there. And so that shows you how having a dipole moment in the molecule, a large dipole moment, can drastically affect what the boiling point is. So look at SO4, for example, and Cl2. SO2 has a molar mass of 64, boiling point of 14. Cl72, molar mass of 71, slightly higher, and boiling point minus 35. And so being polar enhances those attractive forces, those intermolecular forces, and causes the boiling point to be much higher. These next set of molecules, in table 4 are group 5 hydrides. They're a group 5 atom with 3 hydrogens on them. And we see the molar mass increase, the boiling point increases. And I've left the boiling point for ammonia, whose Lewis structure is drawn for us, out for a moment. So if we were to look at that and try to predict what that boiling point might be, as we're going up on these tables, we're getting smaller mass, the boiling point ought to get cooler and cooler, lower and lower. So maybe minus 105, minus 115, 120, something like that. Well, actually, ammonia has a boiling point of minus 28. It's out of kilter, out of whack, out of line with these others. So we're going to have to come back and talk about this. All these are tetrahedral electron geometries, but trigonal, pyramidal molecular geometries or shapes. And so they're very much polar. So they've got dipole-dipole. But there's something special about this dipole-dipole interaction. Let's look at table 5, which are now group 6 molecules with hydrogen. And so we got H2O, H2S, H2SE, and H2TE. And as the molar mass gets larger, the boiling point increases. Now, I've got the Lewis structure for water there. It's not linear. It's really a bent molecule. Those 4 electron domains around the central atom gives us a tetrahedral electron geometry, but the molecular geometry is bent, so it's polar. That oxygen's partial negative compared to those hydrogens being partial positive. So we could draw a dipole moment looking something like that. And that's true for all those molecules. And so we see the boiling point increasing as the molar mass increases. So if we were to try to just using the trends here to predict what the boiling point of water is, it ought to be minus 100. Minus 100 for boiling point of water? That's not the case, because we know it's really plus 100 degrees Celsius. So it's like 200 degrees out of where we were predicted. Something going on here that we need to talk about. One more example. HF, hydrogen fluoride. We're talking about all these in the gaseous phase. Once again, the molar mass increases, the boiling point increases. I've left out hydrogen fluoride, and if the trends were to continue, that HF ought to have a boiling point of, say, maybe minus 105, something like that. Whereas you might suspect at this point, this one's out of line. It's got a boiling point of plus 67 degrees Celsius. So what's going on here? These last three examples, they're all polar. They all have dipole interactions. What's special about these is that they all show the intermolecular force that we refer to as hydrogen bonding. Now, it's not really bonding. So it's not a chemical bond being formed. It's really an attraction. So I wish they called it hydrogen attraction, but they didn't. They call it hydrogen bonding, and we're stuck with that name. So you can identify hydrogen bonding, and that it occurs. We've got a hydrogen directly, covalently bonded to a nitrogen, oxygen, or fluorine, and that hydrogen is strongly attracted to some other nitrogen, oxygen, or fluorine. And so when that happens, there's this very strong intermolecular attraction that causes these boiling points to be much higher than we would expect them to be. Well, why does this occur? Let's think about hydrogen, nitrogen, oxygen, and fluorine. They're at the top of the periodic table. Hydrogen is as small as they come. And we've got nitrogen, oxygen, and fluorine. They're in the upper right-hand corner. They all of them have very small atomic radii. And nitrogen, oxygen, and fluorine have the highest electronegativities of any of the atoms on the periodic table. So between the small size of all of these and the high electronegativity of nitrogen, oxygen, and fluorine, that allows these molecules to be small, these portions of the molecules to be small, so when they snuggle up close to one another, so to speak, and have these very strong attractions. So much so that we give a special name for an intermolecular force is hydrogen bonding. So these three sets of molecules all have dipole-dipole forces, and they also have hydrogen bonding. Let's look at these two last tables. Table 6 shows a series of compounds that we call alkanes. They're all organic molecules, and they contain carbon and hydrogen, and we could also refer to them as being hydrocarbons. And we've already looked at the Lewis structure for methane. It's like this, and it's tetrahedral. And all these molecules are nonpolar, so they only have London dispersion forces. And we can see as the molar mass increases, the boiling point increases, just what we would expect. Methane is a gas at room temperature and pressure. It's not going to liquefy at 1 atmosphere to get down to minus 161 degrees Celsius. Same is true with ethane. Propane is minus 44. Methane is natural gas. Propane, minus 44, it's got greater attractive forces, so it's a little bit easier to liquefy under pressure, and we can do that, but it takes a good bit of pressure to do that, and that's why if you got a LP liquid propane container for your backyard grill, it's made out of steel. Butane, however, has a boiling point of 30 degrees, just barely above ambient temperature, room temperature. And so it turns into gas very readily. And so we can keep it liquefied but with just a little bit of pressure. And that's why your Bic lighter can be made out of plastic instead of having to be steel, like for liquid propane. C20H42 is actually a solid. So these first three were gases, and the next two are liquids at room temperature pressure. And icosane C20H42 is actually a solid at room temperature and pressure. So all of these are nonpolar. They only have London forces. But at some point, those London forces, even though they're the weakest of the intermolecular forces, when we get these very large molecules, the sum of all those little weak forces can add up to something that's very much shows lots of attraction between the molecules. And so icosane has, being such a large molecule, has a high boiling point. It's actually a solid at room temperature and pressure. Let's look at table 7. And these are all organic compounds, and they contain carbon and hydrogen, and also some oxygen in these instances. And I want to look at these and compare and see how they're different. They all have roughly the same molar mass. They're all 44 to 46. They have a variety of boiling points. And if things only depended on London forces, only on the size of molecules, they ought to have all roughly the same boiling point. The question is, why don't they? The first one is propane. It's a hydrocarbon. And all these carbons, they're all tetrahedral. So all the bond angles in this molecule are 109.5 degrees. It's not a perfectly flat two-dimensional molecule. It's nonpolar. So that means the only attractive force, intermolecular force that we have between propane molecules will be London forces. So it's got a low boiling point, minus 44. The next one is ethanol, or ethyl alcohol. And we now got an oxygen in there. So that oxygen, it's got 4 sets of electrons. So that around that oxygen, it's really a bent molecule. So that in the molecule is going to be polar. So it's got dipole forces. So we can see it's got a boiling point of 173 versus that 44. Not only does it have a dipole, it's got a hydrogen that's directly covalently bonded to an oxygen. So that means it's got hydrogen bonding capabilities. And so between those two, that really makes the boiling point be very high. Number 3 is dimethyl ether. Once again, we've got oxygen in there. And remember that it's going to be a bent geometry around that oxygen. So it's bent, plus that electronegative oxygen is going to make this molecule be polar. If it's polar, it's got dipole forces. And its boiling point is higher than propane, but a good bit lower than ethanol. So what gives here is polar. The thing is, it cannot hydrogen bond with another molecule itself. Yes, it has hydrogens. Yes, it has an oxygen. But the hydrogen has to be directly covalently bonded to an oxygen in order for it to hydrogen bond. So that's why we got a lower boiling point than we do ethanol, and yet higher than propane. Next one is methanoic acid. Different functional group. Functional group is what we call those collection of atoms that give it a particular chemistry. It's an organic molecule because it's got carbon and hydrogen, and also some oxygen in here. Got 2 oxygens, so that means it's going to be polar. So we got dipole forces. And the question is, can either one of the 2 hydrogens hydrogen bond? And the answer is yes. And that this hydrogen can hydrogen bond, the one that's directly covalently bonded to an oxygen. And so that's going to give it but having 2 oxygens makes it very polar, and also that hydrogen is something that can hydrogen bond, so it winds up actually having the highest boiling point out of these. And the last one is ethanal. It's polar because of that oxygen. That means it's got dipole forces. Can the hydrogens hydrogen bond? And the answer is no, because the hydrogens have to be directly covalently bonded to nitrogen, oxygen, or fluorine in order to hydrogen bond. So we go back to number 4 for a moment. We'll redraw a couple of these molecules. So the hydrogens are partial positive compared to the oxygens being partial negative. And so hydrogen, directly covalent bonded to an oxygen, can be strongly attracted to some other oxygen. Hydrogen, directly covalently bonded to an oxygen, can be strongly attracted to some other oxygen. So that's how those two molecules can hydrogen bond. Hydrogen bonding is very important. It allows life to be lived as we know it on this planet. If without hydrogen bonding, water, if it boiled at minus 100 degrees Celsius, there would be no liquid water on the planet, and there would be no life. Hydrogen bonding is what holds the double helix of DNA together, those internal base pairs of the DNA that are stacked parallel to one another inside that double helical core. They're held together by hydrogen bonds between the base pairs. Surface tension is an example of hydrogen bonding, where those water molecules on the surface are pulling on each other so tightly versus the air that it sort of forms a skin on the water. That's called what we call surface tension. And so that's why small insects can walk across the surface of the water, or you can float a needle on the water. And so this has been a look at different types of intermolecular forces and looking at molecular examples of where we can find them.